Assalamu alaikum and welcome to lecture number 28. In this lecture we are going to discuss two methods for the IIR filter coefficient approximation. One is called the impulse invariant method and the other is called the bilinear Z-transform method. So you all understand that one of the most important steps in any filter design is the calculation of the filter coefficients. In the previous lecture, we talked about the calculation of the Fourier of the coefficient using pole zero placement method. Other than pole zero placement method, for the coefficient calculation are the impulse invariant method, match Z-transform method, and bilinear Z-transform method. These approaches are more efficient for IIR filter design because they are based on designing the analog filter and then converting the design analog filter into equivalent digital filter. But due to the constraint of the time, we will skip the match Z transform method. So that means we will only discuss impulse invariant method and bilinear Z transform method. So just to recap, that impulse invariant method is based on the following step. We start with a suitable analog transfer function h of s, then we using the inverse Laplace transform, we obtain the impulse response, and then we sample the impulse response, which is h of t, to produce hn of t, and once we obtain hn of t, then we use the Z transform to obtain h of z. So these are the figure showing the impulse response and the corresponding sampled impulse response. So I hope based on the theory you have done previously that you understand the sampling frequency must meet the Nyquist criteria in order to avoid the aliasing distortion. So the four steps of the impulse invariant method are described here. So you understand we start with analog transfer function h of s. So let's assume that we have a analog transfer function h of s, which is equal to c over 1 over s minus p. Then the second step is to obtain the impulse response h of t, and you understand because this is in Laplace domain. So if we apply inverse Laplace on this equation, we'll obtain the time domain of this system function, which is represented by h of t, and that we call it the impulse response. So simply impulse response of this will be equal to taking the inverse Laplace transform of this equation. So we'll get c e power t. Then the next step is to sample h of t to produce hn of t. So hn of t equals to h of t, where t equals to nt. So sampling this in such a way, it will result simply we can say just in this equation we replace t by n capital T, right? And I hope you understand the capital T is the sampling interval, the time between the two consecutive samples. Okay, so that's what you get, hn of t. Now to obtain the desired system function h of z, we simply take the Z transform of c e power nt. So you understand to obtain the Z transform, we sum the signal from minus infinity up to infinity, but this signal exists from 0 up to infinity. So we say okay, summation and running from 0 up to hn of t and multiply by z power minus n. So simply putting the value of hn of t, which is c e power capital C e power p and t, capital T, right? So that's because n is common, so we can take n common from both the terms, so we can write e power t z inverse power n, and we can take out c as constant because c is constant. It's in it doesn't, its value doesn't depend on n. So doing so, the z transform of this will be c over 1 minus e power ptz inverse, or simply we can say that the uh, system function c over s minus p in impulse invariant case results into c over 1 minus e power p capital T z inverse. So generalizing the previous discussion, where we say that in h of s we have c over s minus p, this is the system function in s domain. So in z domain it will be c over 1 minus e power p t z inverse. So generalizing this, we can write that h of s, for example, consists of multiple terms, maybe up to m. So c1 over s minus p1 plus c2 over s minus p2 plus so on up to cm over s minus pm, right? So this can be write in summation as h of s equals to summation k running from 1 up to k running from 1 up to m cks minus pk. You understand pk's are the poles, right? So p's are the poles, and you understand poles are the values of, if we are talking about these Laplace transforms. So in Laplace transform, poles are the values of s for which h of s becomes infinity. Okay, so this is what we have for the h of s. Now generalizing, because h of s, when s consists of h of s consists of single term, that is c over s minus p, then we have this formula, right? This equates to, or this corresponds to this. Okay, so similarly when we have multiple terms here, so again we can write summation k running from 1 up to m ck 1 minus e power pkt z inverse. So for example, if you have a second order section, you understand that while doing the structures, we represent the system function in different forms, such as in second order form, in the partial fraction form, and the factor form, and so on. So we there use the cascade form of the second order section. So if we have second order section, in that case we'll have c1 over s minus p1 plus c2 over s minus p2. These are in the h of s are in the Laplace transform. So the corresponding z transform of this system function will be c1 over 1 e power p1 t z inverse plus c2 over 1 minus e p2 t z inverse. Or on simplification we can obtain this one, this a single expression, right? This for standard second order sections. So let's take a numerical example where we are required to design a digital filter to approximate the normalized analog transfer function h of s, which is given this one, and we have to use the impulse invariant method to obtain the transfer function of a digital filter. We have to assume that 3 dB cutoff frequency of 150 Hz and sampling frequency of 128 Hertz. So you understand that frequency is given in the it's the linear frequency. So if I draw the diagram, it will be something like this. So this is frequency f, and we have to, so for a low pass it will be, the ideal will be this one. Okay, whereas the practical response will be something like, we'll have some ripples here and we have decay of something like this. So for example, here it has value of 1, so at this point it has value of 0.707. Okay, so at 0.707 7, the response is 3 dB. That is, you can write, so expressing in dB, it will be 20 log of 10, a log of 0.707 to the base 10, so it will result into minus 3 dB, right? So the frequencies where amplitude is 0.707 are called the 3 dB frequency. So converting it into radian, it will be something like W of, for example, we represented W of P, so W of P will be equal to 2 pi into 150. So that's something like 300 pi radian, right? Radian per second. So here is the solution. So we obtain H prime of S, which is simply obtained by replacing S with S over alpha, where alpha is basically the cutoff frequency. So this 150 Hertz, so 150 into 2 will be 300, into pi it will be something like 94.4778 radian per second. Okay, so that will be the value of alpha. So replacing S by alpha by S over alpha, so replace here, so it will be S over S square over alpha square plus square root of 2 S over alpha plus 1. So by simplification we obtain alpha square over S square plus square root of 2 alpha S plus alpha square, or we can equate it to C1 over S minus P1 plus C2 over S minus P2 by partial fraction expansion. Okay, so by this way we can find P1 equals to this one. These are the values. Okay, and similarly P2 equals to P1 conjugate of P1. Similarly C1 equals to alpha over, I think you can do the partial fraction by yourself, right? So that's quite straightforward. These values you will obtain and you will find that C1 equals to this one, whereas C2 equals to complement of sorry, not complement, conjugate of C1. So once we know the values for the C1, P1, C2, P2, right, just putting it in this equation, we can find h of z to be this one. Okay, now to keep the gain down and avoid the overflow when the filter is implemented, it is a common practice to multiply h of z by t. Okay, so you know t is the sampling period, so we can easily find from here because we are given the sampling frequency. So 1 hour sampling frequency is basically the sampling period. So on multiplying by h of z by t, or we can also say that by dividing it by the sampling frequency, so the transfer function becomes this one. Okay, and the structure for the resulting system is as shown here. So I hope that will be quite straightforward for you, because there's only involved the partial fraction, which you know already. We have done this so many times. So by using partial fraction we can find the value of the P1, P2, C1 and C2. Once we know them, just by putting in this equation, it will result into the system function as shown here. But to avoid the overflows, we have to multiply the resulting system function either by t, or we can also say that we have to divide the resulting system function by sampling frequency. So we'll obtain this final expression. Another important method for finding the coefficient for the digital filters are the is called the bilinear ZTransform method. This method maps the h of s from s plane into the h of z plane. So the two planes are drawn here. You understand this is the h of s plane. On the x-axis we have real variable, whereas on the y-axis we have the imaginary variable, similar to what we have for the z transform. So based on the Laplace transform, because h of s is system function in Laplace transform, so the if so by the previous knowledge you understand that the poles lying in the left half of the S plane basically corresponds to a stable system, whereas those lying to the right are the system where we have unstable system. Similarly, for the case of the Z transform or the Z plane, if the poles are lying inside the unit circle, then we have a stable IIR system. If the poles are lying outside the unit circle, then we call such a system as the unstable system. So the j omega axis and S plane is mapped onto a unit circle. The left half of the S plane is mapped inside the unit circle. So you can see that these lines, right, some type of oblique, right? So these lines, they correspond to the inside the unit circle, whereas the right half of the S plane corresponds to the values which are outside the unit circle. So right half is mapped outside the unit circle, whereas left half is mapped inside the unit circle. So that means stable analog filter will have poles to the left half of the S plane, so they will lead to the poles inside the unit circle. So that means stable analog filter will correspond to the stable digital filter having the poles inside the unit circle. Now in case of the BZ method, we replace S by K into Z minus 1 or Z plus 1, where K can have value of 1 or 2 by 2, all 2 by T, although because when we use the numerical example, you will see that K is replaced in such a way that whatever value we assign to K, it will get cancelled with the algebraic, just small algebraic manipulation. So that means it's not important whether we keep K equals to 1 or 2 by T, it will result into same. But in this way, replacing S with this expression will result into a filter with not desirable response, or the whatever we want the response or the function from the system, it will not perform in that way. So to overcome this problem, we will use pre-warping. Pre-warping is the way in which we can get rid of this one, and this technique we relate the analog signal frequency, which is omega prime, and the digital signal frequency, which is omega, by this expression. So here we'll have omega prime, which is the analog signal frequency, equals to K times tan of omega T divided by 2, where omega is the frequency of the digital signal and T is the sampling period. So again, K is not important, so we can also skip it, and we can straight away write omega prime equals to tan omega T by 2. So the resulting warping method, which we have expressed here using this equation, is plotted in this graph here. So we can observe easily that for a small values of omega, the relationship is quite linear. Okay, you can see this one from here, right? This is the analog frequency or the continuous signal frequency, right? And this is for the digital signal frequency. So from here we can easily observe that at higher values of omega, the relationship is becoming non-linear. This leads to a distortion which is called the warping distortion. Pass bands for the analog filter on the left hand side are of constant width, right? So these are of constant width. and centered at regular intervals. Whereas if you look at these one, so you see the difference between this one and this one, again the distance between this one and this one, right? So that means the passband for digital equivalent are somewhat squashed version. This effect is normally compensated by pre-warping the analog filter before applying the BZT. So to summarize the BZT method, uh, we say use these are the steps. So use digital filter specification to find a suitable normalized prototype analog low pass filter H of S, right? So for all we will obtain a low pass filter, and then we will transform this low pass filter into, because we are using the frequency selector filter, so we will transform it from the low pass into low pass, and low pass into high pass, and low pass into band pass, and low pass into band stop. So the first step is that we use the digital filter specifications for the analog low pass. Then the second step is determine and pre-warp the band edge or critical frequencies, right? That is the cutoff frequencies, or those frequencies, right? So of the desired signal using the definitions as shown here. So I hope that is the analog frequency will be equal to tangent digital frequency times the sampling period divided by 2. So in case of the band pass filter or band stop filter, we will have two band edge or critical frequencies, that is cutoff frequency 1 and cutoff frequency 2, which are represented by omega prime p1, that's equal to this one, and omega prime p2, which is equal to this one. Then the next step is to denormalize the analog prototype filter by replacing S in the transfer function using the following transformation. Okay, so once we have done this step, then we come and we replace S by omega prime P for the low pass filter. Whereas for the case of the high pass filter, we'll replace S by omega prime P divided by S. Similarly, for the band pass filter, we'll replace S by S square plus omega naught square divided by capital omega S. And similarly, for the band stop, we'll replace S by omega times S divided by S square plus omega naught square, where the additional terms that are omega naught square, right? Because we have defined here omega prime P1, omega prime P2, but we haven't defined them. So in case of band pass filter or band stop filter, we'll have two critical or band edge frequencies, which we represent by W prime P1 and W prime P2. So omega naught square, which is used in the pass band and also in the stop band filters or the notch filters, we define omega naught square equals to omega prime P2 multiplied by omega prime P1. P1 is the cutoff frequency, lower cutoff frequency, whereas P2, omega prime P2 is the upper cutoff frequency, and you understand the lower cutoff frequency and upper cutoff frequency will be used in the band pass filter and band stop filter, whereas omega, which is given here, and also it is given here. So this omega is basically the difference between the upper cutoff frequency and the lower cutoff frequency. So once we do this one, that is we replace S by this, then straight away apply BZT to obtain the desired digital filter transfer function H of Z by replacing S in the H prime of S. You understand, H prime of S you obtain where you replace S by values of these, that is this one or this one, depending upon you are using low pass filter, high pass filter, band pass filter, or band stop filter. So there you replace this and you obtain H prime of S. Now to obtain the digital filter function, that is H of Z, we'll simply replace S by S equals to Z minus 1 over z plus 1. So I hope that's quite straightforward and you can easily do it. So to get the idea how we'll be using these steps, let's have some numerical examples so that we have clearer understanding of how to use these. Okay, so the first example is determine the transfer function and the difference equation for a digital evaluation for the digitally evaluation of the RC filter having sampling frequency of 150 Hz and cutoff frequency of 30 Hz. And we are given that we have to use the BZT method. The normalized transfer function for RC filter is given as this one. So you understand, based on this equation, we can, because we are not told, we are just given the sampling frequency and the cutoff frequency. So do you think it will be a high pass filter or it will be a low pass filter? Okay, can you tell from the given data whether the requirement is a high pass filter or low pass filter? So I hope you think about it, and let's start the solution. Now to solve, let's first determine the critical frequency for the digital filter. So we are given frequency in in linear frequency units, so we first convert it into radian frequencies. So it's simply multiplication of the linear frequency by 2 pi will result into the WP. Then the next step is that we pre-rep this frequency. So to pre-rep this frequency, we use the equation that W prime P will be equal to tangent WP into T divided by 2, right? So, or let me write it. So W prime of P, as we know, is equal to K tangent WP capital T divided by 2. So by putting values, because as I said earlier that K, because when we calculate the K cancels with K, so K, keeping K1 is okay. So by keeping K equals to 1, we have tangent. Then WP is basically this one. So it will be 2 pi into 30 divided by 2 times the 150, 1 over 150, because that's the sampling frequency, and the sampling period will be equal to 1 over 150. So on simplification, we get something like this. The 0 cancels with this one, 3 ones are and 5 are. So we get something like this one, pi by 5. So tangent of pi by 5 will result into 0.7265. Once we know this, then we denormalize the analog filter transfer function to obtain h prime of s, which is so to denormalize h prime of s, we obtain from h of s simply by replacing s with s over omega prime p for the low pass case, and if we with the same condition, if we have to find the high pass filter, then we'll replace s by omega prime p divided by s, if you recall the previous slide. So anyway, because we are finding the low pass filter, so we'll replace s by s over omega prime p, which is 0.765. so if we replace s by this, so looking at this into this equation, we can see that we have only one variable s here, right? I mean, we don't have squares or any other terms, only one term that contains s. So I'll replace s by s over 0.7265. so s over 0.7265 plus 1, and the remaining things remains as it is. So if I take this one common from here, then I'll be left with s plus 0.7265, and because this is double divided, so it will come here. So I think simple algebraic manipulations or just simplification is easy for you, right? I mean, you can do it by yourself. So that's what you get. Now the next step is that we obtain h of z. So how we obtain h of z? To obtain h of z, we say h prime of s should be replaced by z minus 1 into divided by z plus 1. basically k is also here, right? So if I put k here and again here, so you will see it will be it will be divided, k, the term containing k will be divided by the term containing k, so both k's will get cancelled. So that's why it's better we just keep k equals to 1. Anyway, so we get this thing now. That's this here we replace s by s minus 1 over s plus 1. So you can see s is here, so s should be replaced by z minus 1 divided by z plus 1. Okay, so on simplification we'll get something like this, and on further simplification getting the z in the z power minus 1 term, so it will be something like this. Okay, so I hope that's quite straightforward. Okay, simply you first calculate the critical frequency or the cutoff frequency in radians if it is not already in radians. Then you do the wrapping. For wrapping, you equate the analog frequency omega prime p by tangent omega p of digital times t, right? Basically this one is omega p into t is digital, so divided by 2 will give you the pre-wrap frequencies. So once you get the pre-wrap frequencies, then you denormalize the analog filter, and how you denormalize that depends upon whether you are designing the low pass filter, the high pass filter, or the band pass filter. So depending upon that, you replace the value for the s, whether, because in low pass case I'll replace s by s over, let we call it omega prime p, so we'll replace s by omega prime p. But similarly, with the same conditions, if I have to design the high pass filter, in that case I will replace s by omega prime p divided by s. Okay, so that step is, or the denormalizing analog filter step is important. So based on the condition whether you are going for the low pass or high pass, you have to replace s accordingly. Okay, and then this second thing is quite easy, that you replace h prime of, in h prime of s we replace h prime of s by h of z, such that s equals to z minus 1 divided by z plus 1. So this is the BZT step. Okay, so in BZT step you replace you equate h of z by h prime of s such that s equals to z minus 1 or z plus 1. So I think that's easy. Okay, now once you get this one, that's very straightforward. You can get the difference equation simply, because h of z equals to y of z over x of z. So multiplying in the cross, so that means y of z times 1 minus 0.584 z inverse is equal to x of z multiplied by this. So simply taking the inverse Z transform, it will result into this expression. Let's take one more example. Here we are required to design a digital filter to approximate the following analog transfer function. So h of s equals to 1 over s square plus square root of 2s plus 1. Now we are told that we have to use BZT method to obtain the transfer function h of z of the digital filter, and we are given a 3 dB cutoff frequency of 150 Hz and sampling frequency of 1.28 kilohertz. Okay, so because we are given here that we have to design a filter, because the from the diagram we can easily tell that whether it's a high pass filter or low pass. But just looking at this diagram, can you tell whether it's a high pass or low pass? Okay, so because the capacitor is in parallel with the output, so that means the voltage across capacitor will be same as the output voltage. So from the characteristic of the capacitor, we can say that as the frequency increase, the capacitive reactance will decrease, which will result in lowering the voltage. So that means at a very high frequency, the capacitive reactance will be almost zero. So that means it will act as a short. So when the circuit is short, the voltage is zero. So that means it is basically a low pass filter. Okay, so I hope you understand with the 3 dB cutoff frequency and those things. Now to solve this, the first step is that we go for the converting the frequency from the linear into the angular frequency or the radian frequency. So we'll get W of P like this, and once we know W of P, the next step is we are going to find the W prime of P, and you know that W prime of P is basically equals to K times tangent W of P T divided by 2. But because K, if we replace here and also in the next step we replace when we apply BZT, okay, so in that step also and because both the K at this step is numerator, for example, then the K in the next following step will be denominator or vice versa, so it will stand cancel. So that's why it's no need to write the K. So straight away W of P into T, so W of P is your 2 pi times 150, okay, and T is again 1.28 kilohertz is the frequency, so that means the reciprocal of the frequency will be the time, okay, the capital T, so that means capital T will be equal to 1 over 1.28 kilo, or it will be something like okay, so from there you can easily, I hope you can easily find it, or maybe I just write it. So anyway, on simplification you will get some value which is 0.3857. so once you obtain this one, then you do the obtain the H prime of H prime of S. And how you obtain H prime of S? Because you are told that this is a low pass filter, so in case of low pass filter you replace S by S over omega prime P. So again quite straightforward, you just replace this one and then you have this, okay, wherever you have S you replace S by S over prime P, okay. So again here, here and here, on simplification you get omega prime P square over S square plus square root of omega prime P S plus omega prime P square. So on simplification, because you have value for omega prime P which is 0.385 7. So replacing this, so here we'll just take the square of this, which will result into 14 point something like, right, and then you have S square into square root of 2 times 3.857, this will result into this one, and plus the square of this, which is 0.1488. okay. So once you get this one, then you apply the BZT. BZT is simply replacing S by Z minus 1 over Z plus 1. So if I replace S by Z minus 1 or Z plus 1, I'll have 0.1488 divided by Z minus 1 plus Z over Z plus 1 whole square plus 0.545 again for S Z minus 1 or Z plus 1. So I'll get this thing, and on simplification we'll get this thing, and on further algebraic simplification this will result into H of Z equals to this. So I hope that's again straightforward to write the difference equation for this one. So let's have another example. In fact, it's a homework problem. So here we are given the transfer function. We need to find the transfer function and difference equation for the digital equivalent of the high pass RC filter having sampling frequency of 150 Hz and cutoff frequency of 30 Hz. Okay, and you have to use the BZT method. The normalized transfer function for the RC filter is given as this one. So I hope that's straightforward. You can just do it. It's similar to what you have already done. You just have to determine W prime of P, and once you determine W prime of P, you understand for the case of high pass, we'll replace S by omega prime P by S. So in this way you will denormalize the analog prototype. So once you complete this one, then simply you apply BZT, and what is BZT? You replace H prime of S by H of Z, and you replace S by Z minus 1 over Z plus 1. So I hope that is similar. That's quite straightforward because we have already done one example on such problem that was low pass. Now we are going to do it for the high pass. So I think that's all for today. So see you in the live session. Allah Hafiz.